All right, thank you very much, Mr. Chairman, for the kind introduction, and thanks a lot, Jaroslav and all the organizers for bringing us here and also for giving me the chance to present some of my group's work. So, contrary to what I announced in my title and abstract, I decided to narrow down the scope of my talk a little bit to tailor it maybe a bit more to the interest of this audience. And I'll be talking about our work on using single spins as nanoscale quantum sensors and their applications to studying two-dimensional van der Waals magnets. Again, I found that this particular application that we're pursuing could be of particular interest here. And of course, I hope this will also trigger discussions for after my talk. So before getting into this, let me start by acknowledging the people who do all the work. So this is my group. We call ourselves the Quantum Sensing Group. I will, in my talk, probably touch upon things that pretty much everyone of this picture worked on, so I will not go through the individuals. I do want to point out one person. The picture may be too small. This is Clément. He's sitting in the audience here. He's there. He's actually working on one of the projects that I'll be discussing today, namely the imaging and sensing of spin waves in van der Waals magnets, or rather towards that, because we haven't gotten to the goal yet, and maybe you want to discuss with Clément as well later on. Okay, so what we're doing in my group is we're developing quantum systems into sensors, and we want to make them sensitive and robust enough so that we can use them for actual applications outside our actual field of interest, and those are mostly in the field of magnetism. And so we have, I would say, three pillars of activities in my group. We're developing technology, and these scanning probes that you see here in this artist picture is one of these technologies. Then we work on applications, and again, there's quite a spread of things we're doing. This is an example of imaging vortices in a high TC superconductor. We're also interested in looking at anti-ferromagnets, and then those two-dimensional van der Waals magnets, which I'll focus on today. But of course, I'll be happy to discuss any of these other aspects as well later if you're interested. And then lastly, we're also looking into, let's say, foundations of these quantum systems that we're looking at. I'll present the one we prefer afterwards, and you won't be surprised that it's the NV center. So we also do spectroscopy on quantum systems, such as the NV center, to find out some new fundamental properties that may not have been highlighted so much in the past. Okay, so let me jump into this very short presentation of the main workhorse in our activities. And again, I realized this was presented yesterday, at least twice, so I'll be rather fast. So most of our experiments are based on these NV center spins, a point lattice defect in diamond that hosts an electron spin 1. So in the ground state, you have the spin manifold as shown here. And what we like so much about the NV center is that you can optically address that spin, and you can do that even at room temperature. So if we pump the system optically using green light, we can do optical, well, this leads to optical pumping, and it initializes this spin into its ms equals 0 ground state. And by essentially the same process, we can also read out the spin states because they show different brightnesses here in fluorescence. And taking this all together, we can perform optically detected electron spin resonance. So we can come in with microwave driving fields and try to excite any of these transitions. And if we hit them, sure enough, we'll see a drop in the fluorescence of these NV centers, and that signals this spin resonance. And of course, this is a well-behaved spin system, so it reacts to magnetic fields, and those features split linearly as you apply a magnetic field along this NV axis. So here you have your sensor. This is the basics of NV magnetometry, and we exploit the fact that this splitting here is, again, linear with field with a proportionality constant that we know exactly because it's the same for all NVs. G is equal to 2, so this dispersion is 28 gigahertz per Tesla. And so we have a self-calibrated quantitative sensor. That's rather sensitive, and I'll comment on this later a bit more, but essentially if you analyze here signal to noise, you find that you can detect something like changes on the order of a micro Tesla per square root of hertz within a second of data acquisition. We can also do coherent manipulation of these spins, and here I show you an example of a Ramsey free induction decay, exploiting one of these two-level submanifolds here. What we do for these experiments is to initialize into this ground state, create a coherent superposition of this two-level system, and then let this evolve over time. And you see how here with time, you accumulate a quantum phase. And as you change detuning, and I express this here in units of magnetic field, of course, there's also a beating. And this is another way of understanding how we can do magnetometry using quantum manipulation of the NV spin. I bring this forward, I mean, this is, I guess, a trivial example that most of you know. I bring this forward just to highlight that there's a whole tool set of coherent spin manipulation techniques applied to the NV for sensing. And we'll have a couple of talks later in this conference, the next one by Natalie, and then tomorrow by Turno, maybe others which I overlooked, that will discuss various aspects of these. The bottom line is that you can essentially tailor the frequency range that NVs are sensitive to, as well as the sensitivity by applying various pulse sequences. The pulse sequence here is rather simple. As I said it before, green excitation and then these microwave pulses to create the coherent superposition. But for certain applications, this may still be too much. If you're thinking about ideas that exist to miniaturize these sensors into compact packages, for instance, for geonavigation and other things, you want to minimize the number of control fields. And here I would just like to briefly flash a recent result we've had in my group that addresses this issue. This was in fact a chance finding that we had where we realized that if you tune this NV center to a certain regime of magnetic field, you can skip the radio frequency. What that means is that optical pumping, instead of initializing the spin into an eigenstate, it can initialize the spin also in a coherent superposition state. And I should stress this applies to the nuclear spin here attached to nitrogen of the NV center. So this was just a brief flash. I'm happy to discuss this later or describe this in more detail if you wish. The bottom line is that you can perform Ramsey-free induction decay here on a single nuclear spin or also on ensembles using only green optical excitation at room temperature, and you find coherence times here approaching a millisecond. And I believe this could be rather interesting in the future, for instance, for gyroscopes. Okay, so let me move on, and I see I'm a bit too slow, to go in this direction of the nanoscale sensing. So one of these technologies we developed are these scanning probes that host individual NV centers. So here you see an electron micrograph of a all-diamond scanning probe tip. At the very end, you have a single NV center, which I draw here for you. That thing is attached to a quartz tuning fork. That's a force sensor that allows us to do force sensing and bring this NV in close contact with a sample of interest to do magnetometry. There's a bit of engineering involved here. So if you zoom into these tips, those are in fact photonic nanostructures that we're trying to shape in a way that the emission of the NV center preferentially goes upwards to our detector, which sits somewhere up there. The simple understanding here, which is an oversimplified picture, of course, is in an array picture, you see this parabolic shape that just leads to this, and we're trying to place the NV here in the focus of the parabola, so you get this emission upward. If you analyze the performance of this, we realize today with these scanning probes, collection efficiencies, sorry for that, collection efficiencies from the NV to the detector of roughly 12%. That's a number we're quite happy with, and that leads to those sensitivities that I mentioned before. So all of this is by now quite established in my group. It's scalable, it's robust, and this leads me to this one advertisement that we spun this out in the company. It's called QNAMI, and at QNAMI you can actually buy those tips and also fully fledged systems for scanning NV magnetometry at room temperature, but also under cryogenic conditions. And if you want to hear more about that, then let me know later. Good. So then let's go into this one application that I promised of studying two-dimensional van der Waals magnets using scanning NV magnetometry. So those are parts of this class of materials that have this van der Waals magnetic, van der Waals crystal structure, graphene, of course, being the most prominent of them. But since the discovery of exfoliated monolayer or few layer graphene samples, people have discovered that there's a whole range of materials that have the similar crystal structure, can be exfoliated down to the monolayer, and have various properties going from semiconductor, metals, superconductors, etc. But it was only in 2017 that also magnetic van der Waals materials were discovered, or rather isolated down to the monolayer, and where it was shown that even in this mono or few layer limit, magnetism and long-range magnetic order can persist in these materials. And this has created quite a bit of excitement in the field. For one, it complements this list of van der Waals materials so that you can now generate functional devices and bring those together to essentially explore new physics, for instance, proximatizing superconductors with such magnets. But also from the pure magnetism point of view, this is very exciting because those van der Waals magnets, they essentially realize near-perfect spin lattice models, which turn out to be highly tunable, either by composition or field or strain. You can actually affect the Hamiltonian parameters that govern the physics of these spin lattices. So that's rather exciting, and combining this with what people are doing in the field of van der Waals physics, for instance, twisting or proximatizing, I think there's a lot of exciting physics in magnetism ahead using or building on these materials. Now, there is a challenge, or was a challenge in this field, and that is that it's extremely difficult to address magnetic order in these systems on the nanoscale. And that, of course, has to do with the very weak magnetization at hand that doesn't lend itself to the more traditional imaging and sensing techniques. In fact, in the beginning, when these materials were discovered, pretty much the only tool around for imaging was magneto-optical Kerr effect imaging, so an optical technique that has resolution limited by diffraction. And here you see an example of one of these first compounds that was discovered, chromium triiodide. And here you see such a flake that breaks up into two domains, signaled here by these red and blue patches. You see that one can image this magnetism, but of course with much reduced spatial resolution. And also not all van der Waals magnets are Kerr active and can be addressed using this technique. And this is what motivated us back then, so roughly in 2018, to go into this field. And for this, we collaborated with my colleague Alberto Morpurgo from Geneva, who provided us with first samples, and we started exactly with that compound, chromium triiodide. So here is just to flash the results from that time. This is one of the samples that Alberto and colleagues prepared for us. This is chromium triiodide, a bilayer and a trilayer flake. I should stress, and this is illustrated here, that those are extremely fragile samples. They essentially self-destroy immediately under atmosphere. So you need to encapsulate them very carefully that they remain intact. So once we had these, well, we put them into our system. Here, incidentally, I should say these materials order at rather low temperatures, in this case at 40 Kelvin. So we brought this into our cryogenic scanning NV magnetometer and performed imaging. And well, lo and behold, we saw stray fields emerging from these flakes. You see here that the bilayer shows almost no stray field. That's because adjacent layers show anti-ferromagnetic ordering. The trilayer, however, does show a stray field. And you see immediately that the stray field only comes out at the edge. That is, however, exactly what you expect for a fully polarized two-dimensional magnet, which in this case, for an out-of-plane magnetization, you can just represent by an edge current going around the flake, and that generates this field. Still, we're typically much more interested in the underlying magnetization pattern, but luckily one can actually invert that problem. So we can map, we can transform this measured stray field map to the underlying magnetization pattern by a technique called reverse propagation. I will not go into the details here. I just want to stress that this is not always an easy task to do, in part because this is not always a one-to-one mapping, so there's not always a unique solution. But here in the case of an easy access out-of-plane magnet, there is such a solution, and here you see the outcome of it. I also want to highlight that we've been working on this inverse problem for quite some time. Here are some references, and we're today actually more routinely applying machine learning algorithms to optimize that and also improve the quality of this reconstruction. Good, so what can we do with these images? Here is another example where we looked at domain reversal in this very same flake. You see here this splits up into this red and blue domain, which signals, of course, spin up and spin down. And you can compare this now to this image I've shown you before, this magneto-optical Kerr effect, and I hope you appreciate right away the increase in spatial resolution, but also the quantitative nature of this image. Note that the color bar here is really in spins per nanometer square. That's the quantity you're oftentimes interested in. So this was the basis of our experiments. And now building on these results, I think there's really a lot to be explored in van der Waals magnetism, in fundamental understanding of magnetic order, but also engineering of spin textures. I do want to highlight more specifically one direction that we have, which is to try to use NVs to sense spin waves in these van der Waals magnets. How this works exactly, you will learn from Turno tomorrow, so I will not go into this. And you also heard about this from Eugene yesterday morning, how one can use essentially noise spectroscopy of the NV center, how can you use relaxometry of the NV center to do noise spectroscopy of high frequency noise. And it turns out that oftentimes this noise lies exactly at the NV spin transition frequency, so the NV is quite amenable to this task. So one goal we have here is to engineer waveguides for spin waves. It has been long known, also in more classical magnetism, that domain walls can actually act as such waveguides if you're dealing with a magnet with strong uniaxial very anisotropic material. Then you have strongly gapped Magnum modes in the bulk, but a non-gapped mode here in the waveguide, and this can then propagate along this domain wall. And of course, the long-term vision for this is to use this to couple remote NVs. Good, so this is the vision, and I want to stress once more that I think NVs are quite uniquely positioned to address spin waves in van der Waals materials, because pretty much no other technique, to my knowledge, has the required sensitivity and bandwidth for that. But in order to go in this direction, we need better materials. This material here, chromium triiodide, I mentioned it already before, is really very finicky, it's very brittle, it exfoliates in very small flakes, and it has a very short lifetime. There's a lot of reasons why it's very difficult to work with that. And here comes, therefore, this new player that I want to introduce to you, and some new results from my group, with this material called chromium sulfur bromide, or some people call it also the CRISPR of magnetism, that has recently been discovered and I think pioneered by Corey Dean and Xavier Roy at Columbia, who also sent us those samples. Now, this is a rather interesting material for various reasons. So first off, what is the magnetic order? This is again an in-plane magnetized, well, not again, this is now an in-plane magnetized material where a given layer orders ferromagnetically, but adjacent layers show anti-ferromagnetic correlations with respect to each other. This material cleaves beautifully into very large flakes. You see an optical micrograph, so you get flake sizes of tens of microns, which again addresses this materials issue I mentioned before. And all of this is air stable. It's air stable down to the monolayer, as I'll show you later on with data. I should also say, and I forgot to say that within this plane, actually, there is a preferred axis, so it's not a fully anisotropic in-plane magnet. It has a preferred axis, and it turns out to correspond to one of these cleavage axes. The B axis is where the magnetization naturally wants to point to. And then lastly, I want to say that this material has a interesting and still not fully understood phase diagram. So this is sort of a rough sketch of magnetism in chromium sulfur bromide as a function of temperature and magnetic field. You have various transitions, for instance, metamagnetic transitions, where you can drive this into a ferromagnetic order, but also this rather interesting interferromagnetic phase here that happens roughly at 150 Kelvin, where it turns out that neighboring layers become uncorrelated, but you maintain ferromagnetic order within each layer. At the same time, you're losing anisotropy. So this is something that could mimic possibly an XY magnet, but that remains to be seen. Okay, so we looked at this material for all these reasons. Here are some data, and I show you now all these reverse propagated images and not the bare NV magnetometry, just for clarity. So here are a couple of flakes again, bilayer, trilayer, monolayer. You see all of them show a magnetization. The bilayer, again, of course, zero magnetization at low field, but we can flip it into a fully polarized state here by applying a field. And that gives us, in all cases, a magnetization in quantitative units, and we can then plot this, essentially the magnetization per layer as a function of the layer number in these samples. And this revealed the first surprise, and something we can currently not quantitatively explain, and I'd be very happy for input, namely that the magnetization per layer seems to scale approximately linearly, essentially, initially, and then saturates only after roughly 5 layers to the expected value of a fully saturated chromium sulfur bromide flake that we can, of course, estimate from theory. So this suggests, of course, that the intralayer exchange coupling, the interlayer exchange coupling plays an important role for stabilizing the interlayer ferromagnetic ordering, but how exactly that works, again, we don't currently understand. We were also able to look at this magnetization as a function of temperature. Here you see two examples for a monolayer and a bilayer. Here going to this critical temperature of 140 degrees. So this is the nail temperature where the correlation between adjacent layers vanishes. But we see that there's clearly still some magnetization remaining beyond that. And that's exactly this intraferromagnetic phase that I mentioned before. Again, work is in progress to understand that further. 3 more minutes? 5 more? Okay, good. I'll speed up. So I want to show you a last set of data where we looked at this metamagnetic transition in chromium sulfur bromide that I mentioned before. This is essentially a spin flip transition where by applying a magnetic field, you turn this antiferromagnetic order to a full ferromagnet. If you look at this roughly in the transition region, you find that there is a coexistence between ferromagnetic and antiferromagnetic phases. This is again one of these quantitative images. And we can actually look at how this coexisting region or the wall that separates the two propagates as we change magnetic field. This is shown in this movie here. So it's just a sequence of images with decreasing field that shows you how this phase propagates through the bilayer. I like that movie, first off. We think it does contain some interesting physics. You see how this thing really seems to, this wall seems to stretch through that material, a bit like a soap bubble that has some boundary conditions and tries to warp around these corners and then collapses very, very quickly. You also see that there is very little roughness, which indicates little pinning and disorder in this material, which is also indicative of the quality of these flakes. And lastly, if you look at the part where this ferromagnetic phase collapses, there is a rather peculiar shape. This is again this ferromagnetic phase that collapses into a smaller and smaller object and then vanishes. It has this cusp, which is another feature we don't currently understand. And I'll be very happy to get input from people from the magnetism community, how we could possibly model and understand that. We have some ideas. For instance, these could be two parts of a domain wall of opposite helicity, creating here a Bloch point, but we don't have any, let's say, more deeper theory to support that. Okay, do we have 1 more minute? Good, so 1 more minute to just flash something for the NV enthusiasts in the audience, and I know there are a couple of them, which connects to this temperature-dependent measurements. So we've realized for a long time over the last years that NVs actually, at low temperatures, they perform well, but not always equally well. There are certain regions of magnetic field and temperature where we see very poor NV magnetometry performance. That's something we looked at over the last year, essentially. This is data that shows you the NV photoluminescence intensity as a function of magnetic field and temperature. And you see this rather peculiar shape here, which, and this is what I want to conclude with which we can by now fully and quantitatively understand using a rate equation model, essentially Lindblad-Master equation, that takes into account the level structure of the NV center. I will not go through individual steps here. We can talk about this later on. The takeaway message is we fully understand that this is our theory model that essentially captures what we see experimentally. And now that we have that understanding, this helps us a great deal in our low temperature NV magnetometry experiments because we know now which regions to avoid. So everything that's dark here, you can essentially not measure at, so you want to go out of there, or you want to tune the NV so that it performs better, and you can do that, for instance, by going to different strain values. So these are data for one strain value, low strain, and high strain, so you see that you can sort of shift these bad regions here. Okay, that was the short last point I wanted to make. With that, I'm done, and I thank you a lot for your attention, and I look forward to your questions. Oh, and we have open positions, as everybody.